Hello everyone, welcome to Civil Engineering Geeks. In this lecture, we will see the definition of the equilibrium and what are the equilibrium equations available and their applications in strength of materials. Beginning with the definition of equilibrium, it is a state of balance where number of forces acting on a body gets cancelled out by each other and there won't be any change or disturbance occurring on that body. To understand this better, suppose we consider a body lying on a ground and there are three external forces acting on that body. These forces will try to move or disturb the body, but we can't say in which direction it will move. It can move in the upward direction due to the force F1 or towards its left due to force F3 or towards an angle theta due to force F2. We know that the object cannot move in all the three directions at a time. So, to find in which direction it could possibly move, we should restore these three forces to one resultant force. To do so, let's initially assume a resultant force which is acting between F1 and F2 at an angle alpha to the horizontal axis. Now we can say that the object will move along the direction of the resultant force. But our aim is that the object should not move even if the forces act on it. So that is why we provide supports. When the support is provided, it will develop the equilibriant force to cancel out the resultant force which is acting on the body. And this equilibriant force are nothing but the reactions that are developed by our support to resist the external force, in this case the resultant force. This resultant force can be resolved into two components as R cos alpha in the horizontal direction and R sin alpha in the vertical direction. To nullify this resultant force, the ground, that is our support, will develop an vertical reaction of magnitude R sin alpha and the horizontal reaction of magnitude R cos alpha. And now we can say that the object is in equilibrium, or other words, the force F1, F2 and F3 applied on the object is nullified or cancelled out by the reactional force or the equilibriant force developed by the support, and hence the object is stable or unmoved. Moving on to see the equilibrium equations available in civil engineering. There are generally three equilibrium equations. The first one is the summation of all the vertical forces or the forces in the y direction should be equal to 0. And the next one is summation of all the horizontal forces or the forces in the x direction should be equal to 0. Finally, we have the summation of moments in the member or an element at a particular point is equal to 0. These are the three important equilibrium equations which will be helpful for you to solve almost half of the strength of material problems. Let's now learn about the application of equilibrium equation in strength of materials. To understand the application better, let's first consider a point A and there are three forces that are acting on it. Now we are going to write the equilibrium equation for the given point. Let's resolve the force F3 before writing the equilibrium equation. Now let's consider the first equation, summation of vertical forces equal to 0. We will get plus F1 in the upward direction. We are assuming the upward direction forces to be positive and downward direction forces to be negative. So we will get plus F1 in the upward direction minus F3 sin theta in the downward direction, that is equal to 0. So F1 minus F3 sin theta equal to 0. From this we will get F1 is equal to F3 sin theta. We'll keep this as our first equation. And moving on to our second equation, we have summation of H equals to 0. That is summation of all the horizontal forces is equal to 0. From this we will get plus F2 in the rightward direction. We are assuming rightward direction forces to be positive and leftward direction forces to be negative. So we'll get plus F2 in the rightward direction minus F3 cos theta in the leftward direction equal to 0. From this, F2 minus F3 cos theta equal to 0 and F2 is equal to F3 cos theta. And this is our second equation. We can now tell that for the given point A to be in equilibrium, it has to satisfy those two conditions or the equations. Okay, now one can ask why we didn't use the third equilibrium equation, that is summation of moment equal to 0. That is because summation of moment equal to 0 can be used only when the applied forces are capable of creating a moment at a point. But here we have only one point and all the forces act at that point, which means these forces don't have perpendicular distance to that point. And what happens when there is no perpendicular distance? There is no moment, because m equals to f times perpendicular distance. Here perpendicular distance is 0, so we will get moment equal to 0. We will see one more example where we can use all the three equations. Suppose we have a beam of length L. In this beam, we have F1 force acting in the downward direction at a distance of L by 2, that is the midpoint of the beam, and F2 force is acting towards left at the end of the beam. Now we are going to find the position of the resultant force from any reference point in the beam. Here I am assuming the reference point to be at the start of the beam, and resultant force is assumed to be acting at a distance of x meters or x from that reference point. And it is also important to note that the resultant force is not going to act in the vertical or in the horizontal plane. Instead, it is going to act at some angle theta, because we know that it is the net reaction of the vertical and the horizontal force. Now let's plug in our equilibrium equation and find out the reaction value. So using our first equation, that is summation of vertical forces equal to 0, we will get F1 is equal to Ry. Ry is nothing but the vertical component of the resultant reaction, and Ry is nothing but R sin theta, so we will get F1 is equal to R sin theta. And using the second equation, that is summation of H equals to 0, we will get F2 equal to Rx, which is F2 equal to R cos theta, and therefore we will get R is equal to F1 by sin theta or F2 by cos theta. Both are right. So this is it. Can we say the beam is in stable condition? No. Why? Because in the previous case, we know that all the forces act at one point, but in this case, R can act at any point in the beam. So finding the position of the resultant force is very important in this case. That is nothing but the distance x from our reference point. To find this, we will use our third equilibrium equation, that is summation of moments at the reference point is equal to 0. Since we have already found Rx and Ry values, we will straight away write the moment equation for the considered reference point. While writing the moment equation, we are going to consider the counterclockwise moments as positive and clockwise moments as negative. So what we will get? We will get minus of F1 times L by 2. L by 2 is nothing but the distance between F1 and the origin point. We are using minus sign because F1 is going to create a clockwise moment to the reference point. Then we will get plus Ry times x. X is the distance between Ry and the origin point, and it is going to create a counterclockwise moment. Then F2 times 0, because F2 is acting at the axis of the origin point. There is no any perpendicular distance to that point. So F2 times 0 minus Rx times 0. Rx is also acting at the axis of the reference point. All this is equal to 0. That is summation of moments at a particular point is equal to 0. In this equation, we can substitute F1 equals to R sin theta as we found earlier, and Ry equals to R sin theta as well. So after solving this, we will get x equal to L by 2. So we got the value of x. Now we can conclude that when the resultant acts at a distance of L by 2 from the origin at an angle theta to the horizontal axis of magnitude F1 by sin theta or F2 by cos theta, then the beam will be in stable condition or in equilibrium position or unmoved. Great. Now I have a quick question for my viewers. Is it possible to find the value of theta for this problem? If yes, then how and what is the value of theta? Do comment your opinion below in the comment section. Okay, that's the information I wanted to give you in this video. Hope you found some value in this video. If you did, make sure you drop a like and share it with your friends. If you're new to my channel, you can make sure to subscribe it for more upcoming videos. Thank you and see you everybody in the next video.